Welcome everyone to the Support Vectors meetup. Today is, I believe, September 11th. This is 7:15 p.m. here in California. And this meetup series is organized by Support Vectors AI Training Lab. We provide training in various topics of AI. And this Wednesday paper reading is a weekly outreach. Usually we cover a paper that our community, our learning community has suggested. And now you're, as part of this meetup, you're part of our learning community. So if you're new here, then of course, a very warm welcome addition to our learning community. For the last weeks, we have been covering various topics in natural language processing. So it was pointed out that perhaps it's time to pivot and for diversity, now focus on some computer vision models and multimodal models. So we are going to do that today. The topic for today is this paper, which just came out fairly recently, about 2 weeks ago, which is Sapiens, Foundation for Human Vision Models. This is I consider this to be a very sort of a good paper and worthy of attention. It has achieved something that is as close to being a foundational model for human images as, and we'll cover it in great detail. This paper needs a little bit of a background. You need to know masked autoencoders. Now, for the benefit of people who don't know masked autoencoders, I'll give a small background on masked autoencoders as we make progress with this paper. So once again, the paper we are talking is Sapiens, Foundation for Human Vision Models. So the word sapiens, as these authors point out, it refers to, oh, so hang on. Let me situate myself in the writing desk. Sapiens. Now, is the screen big enough, folks? And readable?
Yeah, it was better before, Asif, a little bit more.
Little bit.
Yeah.
All right.
That's too big. Yeah, too big. You can good. Yeah, that's perfect.
Okay. So sapiens, the term, it pertains to or resembling modern humans. Okay. So we are the Homo sapiens. Apparently, there are other human beings, not so modern, Homo erectus and Homo so on and so forth. Like our old cave-dwelling ancestors. So we are going to, this paper delves about this, but though I should imagine it should apply to all Homo species, all of our things. And so now the particular thing about this paper is it limits itself only to pictures of human beings. Whether they are images or videos, it limits itself to human beings. That is something important. It tries to build what could be practically the foundational model for humans. That's why it's called sapiens. They call this sort of models the sapiens. Now, what is a foundational model? Just to whet your recollection, a pre-trained foundational model is a model, for example, like BERT, is a model that can be used successfully or with certain degree of success for many downstream tasks. You can fine-tune it for downstream tasks, or you could use it as it is with reasonable success. And if a greater accuracy is needed, you could fine-tune it, right? So that's the concept of a foundational model. Here, they're looking at 4 downstream tasks, which are very common in computer vision. One is the pose detection. So how would you detect the pose? Let's look at this. So I'm going to highlight the columns here in this image. Image is there. And as you can see, they're looking at a few images. 4 images. One is an image of a lady, another is that of a child, another is that of a young lady, and the other last one is that of a couple, young couple. So we are going to, I suppose, just get into this to see what they are talking about. Let's start actually from this one, the normal. What is a normal? In computer vision, you say the normal stands for the following. Suppose you have a surface. At any given point, the direction, this is the normal vector. The direction that is perpendicular to the surface at that point is the normal vector. And so the normal detection is basically saying at what places are we getting the normal vector to have a high value, I suppose, are pointing in a direction that is sort of, you take one direction and then you say, how close is the normal vector to that particular direction? Right? Here, it seems to be the up direction. The depth is quite, again, interesting. The depth says it is literally the straight depth. So suppose you have a person, let's say that you're looking from this direction and you have a person. So then this area would have the lowest depth, front would have the lowest depth. Then the next layer would have a greater depth. This would have a greater depth, and so on and so forth. And you can keep going. And then you would say this area is even, you have to go deeper into the surface if you're looking in this direction. And then finally, if you want to go here, this would be even deeper. So this is a depth understanding. Now, if you look at this first picture, it is clear that if you stand like this, if you were to take a pose like this, you can very clearly see that your hands are sticking out. And it shows up in this picture because the depth perception usually is given sort of as a heat map, right? And the brighter it is, the closer it is to you, the less the depth. And the darker it is, the deeper or the further away from you it is. So that explains the depth part of it. It's again a classic computer vision task, given an image to estimate depth or video to estimate depth. The next thing that you're looking at is the segmentation. What does segmentation do? Segmentation takes a set of classes, let's say hand, arm. In this particular case, you have the arm, you have the hands, then you have the right arm, left arm, right hand, left hand, hair, face, then clothes, and so on and so forth. And if you look at the segmentation, that's what it is doing. It's recognizing, and here they have gone further. The lips are also one of the classes they're searching for, one of the things they're looking for. And in this image, all of these images, you can see that the lips have been detected. So this process of taking an image and within that image, finding the things that you're looking for is called segmentation. Right? It again, in computer vision, is ubiquitous. For example, if you're trying to have a self-driven car, you would want that car to look at the scene in front of it and around it and immediately segment it to tell that this is the road and there's a pedestrian crossing the road, isn't it? And so on and so forth, or that there's a traffic light coming or a stop sign coming. All of those things are achieved through segmentation. So that's the job of segmentation. The next task that is here mentioned is, I suppose I'll color it with another color. Let's try luck with green. Pose. So pose is literally pose. Like it is the positioning of specific key points. So for example, if you're looking at hand, if your hands are crossed, It means that you're observing the way your hands are, the way your fingers are, they define the pose. And those fingers, those points on the hand, they're called what are called key points. And the location of the key points help you define a pose. So for example, if I were to raise my hand like this, then obviously if there are key points here, its location relative to my nose would change. It wouldn't be below my nose, it would now be above my nose, right? Or to the side of my nose. So what you do is whenever you talk about a pose, you do it through the detection of key points. These key points are salient features that you expect in an image, especially for human beings. It would be the lips, the nose, the eyebrow, the eyes, the face itself, right? The shoulder blades, the shoulder position, the hands, where are the hands, and the fingers, and so on and so forth. So they make up your key points of interest. Now, this paper is interesting, and it has become customary these days for people to present a paper, and even before they come to the abstract, to present their salient achievement in a figure that brings home the main message. I suppose it's an invitation to read the paper or realize its importance right away, the key contribution of the paper right away, which it does amazingly well. If you observe this paper, and let's read this image, let's read the caption to the image. Sapiens models are fine-tuned for 4 human tasks. 2D pose estimation, which we just saw, a body part segmentation, which again we talked about, depth prediction. We are seeing that in the second column from the right, and normal prediction. By normal, by the way, it's the normal vector, is the normal prediction. Our models generalize across a variety of in the wild face, upper body, full body, and multi-person images. So what it says is that they have trained a model. They may have trained it on certain human faces, but they mention that it hasn't just gone and memorized those faces. It's not overfit to it. It does generalize across a variety of in the wild faces. So they tried out experiments by taking faces that this model wasn't trained on to see, and full body and multi-person images, to validate that it is truly learning. It's truly able to generalize to them. Right? So when you see this, the first thing that occurs to you is, now what is the big deal? Right? Why should you care about reading this paper? And I suppose the big deal is to realize that you are creating one set of models to do all of it. You see that? Right? There is a common approach, a common algorithm they are suggesting, a common neural architecture they are suggesting, and they're saying that this neural architecture or this approach to modeling it can solve a fairly wide variety of tasks. This is to be contrasted with prior approaches where for pose detection, people would create a model. For segmentation, they would create a model. For depth, they would create a model. And for normal detection, normal prediction, they would create a model. So people had task-specific models. It wasn't that easy to generalize and do everything like this. In particular, in the context of human beings, human faces, this is a non-trivial contribution. This is quite a non-trivial contribution, which makes this paper really worth studying. It's just 2 weeks out, and I haven't seen too much talk about this paper yet on the internet, but to me, it appeared as though it did deserve more. It was suggested by somebody in our AI learning community, support vectors. One of the members suggested that, could you please explain this paper? And that brings us here. So here we go. Let's read the abstract. We present Sapiens, a family of models for 4 fundamental human-centric vision tasks: 2D pose estimation, body part segmentation, depth estimation, and surface normal prediction. Our models natively support 1K resolution inference and are extremely easy to adapt for individual tasks by simply fine-tuning models pre-trained on over 300 million in the wild images. That's a lot of images to be pre-trained on. Now, observe something interesting. They're training on 1K high resolution, right? They support inferences on 1K. What is 1K? Basically, what they're saying is you can feed it images 1024 pixel images, right? I suppose 1024 by 1024 pixel square images, and it should work just fine, right? Which is a much higher resolution. Typically, models, if you remember, are typically 64, 128, right? Or 220, 228 or 224, or something like that. These are the usual resolutions at which a lot of the computer vision tasks are done. So it's a bit striking right out of the gate that they're talking of fairly high resolution. As computer vision algorithms go, they're talking of a fairly high resolution images that you can do inferences on. Now, they go on to say, we observed that given the same computational budget, self-supervised pre-training, and so I'll highlight a key word here. They're saying self-supervised pre-training on a curated data set of images significantly boosts the performance for a diverse set of human-centric tasks. Okay? So this observation is a key contribution. What they're saying is that first is self-supervised. If you're going to deal with 300 million images, it is prohibitively expensive to sit and label them or do anything with them, annotate them, right? So you have to take a self-supervised approach. Now, if you think about natural language processing, for example, that has been the norm. For example, how do you train the BERT? You take a masked language model. You go and mask a few words in a sentence, and then you ask BERT to predict what it is, right? And that's how you would pre-train a BERT model. Once you have pre-trained a BERT model for natural language tasks, you can do a lot of natural language tasks downstream with it. Right? And that is in a way, the NLP equivalent of a foundational model. You consider BERT a foundational model. BERT and all its variants. You can use it for many purposes. So this paper, in a way, tries to introduce something, the equivalent of BERT, but specific to human images and videos, namely the Sapiens. Now, the point they're making is when you scale up and train on so many images, you notice that the performance goes up. You observe a significant boost in performance. By the way, by performance here, they mean model performance. They don't mean they don't mean like how fast the inference comes out, right? It's not the latency they're talking about or the throughput or whatever. They're specifically talking about the machine learning perspective, how well the model performs. The resulting models exhibit remarkable generalization too in the wild data, even when labeled data is scarce or entirely synthetic. So one of the interesting things is, as we will see for some downstream tasks, you can create some label data, fairly small set of label data, and you can go, and which is common, right? When you fine tune for specific tasks, you do supervised learning. But to do supervised learning, one of the key things they observed is that you can get away by using synthetic data too, right? So that's another contribution. Our simple model design, and this part I felt was really to the point. Our simple model design also brings scalability. Model performance across tasks improve as we scale the number of parameters from 0.3 to this. So by the way, this scalability is again not in the traditional computer science scale sense that how many requests can you pass through the machine. By scalability, they mean from the neural scaling laws perspective. What they're basically saying is, if you take this basic architecture, neural architecture, and you scale it up in terms of the number of parameters that you have in the model from, let's say, a 300 million parameter, that is 0.3 billion parameters, to 2 billion parameters. Right? What you observe is that the model performance goes up, right? As the models become or develop more and more parameters. So that's an important point. Right? Sapiens consistently surpasses existing baselines across various human-centric benchmarks. So now this speaks to the results part of it. So they have a model that does well, and they point out that objectively, if you look at the benchmark, it actually achieves the new state of the art. Right? It beats the existing whatever was the state of the art, and we'll see that in a little bit. So now let's go into this paper and how it goes about doing it. It's a relatively short paper, but this paper, as great papers do, it sits on the shoulder of a lot of other prior work. One important prior work that is needed to understand this paper is the masked autoencoders. And we'll go into that, but let's first read the paper itself, and then we'll go to the background. So, but before we go into the background, it suffices to say that masked autoencoders are, amongst other things, they are machines that can create, given an image or video, given an image, they can create a vector representation which exhibit very robust and good qualities. Like, for example, if you have lots of cats and dogs and horses, you will observe that in the representation space, latent space, all your cats are clustered. And all your dogs are clustered and the horses are clustered, right? So it has a fairly good semantic understanding of what is there in the image, but we'll come to that. So let's read the introduction. Recent years have witnessed remarkable strides towards generating photorealistic humans in 2D, 2-dimension and 3-dimension. The success of these methods is greatly attributed to the robust estimation of various assets such as 2D key points, fine-grained body part, segmentation, depth, and surface normals. However, the robust and accurate estimation of these assets is still an active research area, and complicated systems to boost performance for individual tasks often hinder wider adoption. Moreover, obtaining accurate ground truth annotation in the wild is notoriously difficult to scale. So they make two things. First of all, you're making models, very specific hacks or specific models for each of the tasks. And the other is it's notoriously hard to get annotated data at scale. It's very expensive. So they go on to say that their goal is to a unified framework models to infer these assets in the wild to unlock a wide range of human-centric applications for everybody. So see, it's a topic we have discussed in our paper readings before. Generally powerful, well, I should say, general powerful models tend to, in the longer run, outdo very specific models. If over the years, we have done many such findings, we have observed a pattern emerge. And this pattern is well observed in our space, that if you create a really good, robust general purpose model, quite often it will outdo very specific models, right? So, and you will see some of that here. So we argue that such human-centric models should satisfy 3 criteria. So they mentioned the 3 criteria that they want to focus on. 3 criteria: generalization. Of course, if you build a model and it doesn't generalize, it's basically overfitting. Right? It should be able to generalize. It should have broad applicability. That is inherent to the definition of a foundational model. Right? So what they are saying is, it would be good to build something that essentially is a foundational model for this group of tasks. Right? So it has broad applicability and high fidelity. Right? It should work with reasonably high thing. So generalization ensures robustness to unseen conditions. So for example, if you have trained people's faces with certain backgrounds, if I give you a completely different set of people, culturally, racially different, and with entirely different background, right? Trees or mountains in the background. it should nevertheless be able to generalize and work well in those situations. That's what they're saying. Broad applicability indicates the versatility of the model, making it suitable for a wide range of tasks with minimum modifications. So that is it. In other words, it should have the qualities of a foundation model. High fidelity denotes the ability of the model to produce precise, high-resolution outputs, essential for faithful human generation tasks. Again, like it should be high-res. It shouldn't be that it creates an output that's very blurry, right? Or it says that, okay, here is your hand, and it just puts a big circle around where the hand should be, but hand is somewhere in there. It shouldn't be like that. It should be much more precise. This paper details the development of models that embark. Okay, so there's a lot of things that I'll skip over in this. Now, we'll start from here. We want to build a model that is self-supervised, right? Somewhat in the style of BERT, but for human images. So amongst various self-supervision methods for learning general purpose visual features from large data sets, we choose the masked autoencoder approach. Right? So now the question is, what is the masked autoencoder approach? We'll go into it immediately. And they choose it for its simplicity and efficiency in pre-training. Very much true. The MAE, which I'll explain, are endowed with a certain degree of simplicity. And also, they work very efficiently because they are sort of encoder models. They're very good use of encoder, decoders, etc. And so these are, by the way, when I mean encoder, decoder, just to give you a heads up, these are all transformer-based models. They're not CNN. We're not talking CNN here. We're talking transformers. MAE, having a single pass inference model compared to contrastive or multi-inference strategies. So what they're saying is that we are not going to use contrastive loss function and or use some complicated multi-inference strategy, et cetera, et cetera. Okay. Now, they go on to say that and so this statement is important, and I highlight it in the paper. We choose the masked autoencoder for simplicity compared to, and not use contrastive. For high fidelity, in contrast to prior methods, we increase the native input resolution of our pre-training to 1024 pixels, resulting in a 4x increase in floating point operations compared to the largest existing vision backbone. So what they're pointing out is that people are not used to training with input images this high res. So that's another interesting thing. You should get an idea that if you increase, why do we not increase the resolution of the input images? Because in a visual transformer, if you remember, just to give you a background of a visual transformer, suppose you have a picture and here is a cat. Right? So what you do is you take this image, the whole image of a cat, and you would create, using the visual transformer method, for example, you would break it up into lots of patches, 16 by 16 patches, let us say. Lot of patches, whatever size that you do. Right? Now, what happens? The more pixel you have, the more patches you'll get. Now, each of these patch is a token, TI. The ith patch is a token. And so the higher the resolution of your image, the more the tokens, T0, T1, Tn. So your total count of token will explode, right? So what does that mean? Suppose you have n tokens, you realize that if you're using a transformer architecture, because you have the KQ, if just to whet your recollection, No, sorry. Do we remember this function, right? The attention is this, right? Because there is a quadratic term here, because this is a quadratic term, remember there's a dot product in attention. And this is a point. If anybody would want me to explain this, and this is not already familiar to you, do let me know. But I'm looking at everybody here. I can pretty much say that most of you have been there in my discussion, in the in-depth discussion on attention in the transformer paper. Attention is all you need. So self-attention. So what does it mean? You have quadratic complexity here. There are n key vectors, n query vectors. And each of them, now you have a quadratic attention. There's a quadratic cost in an attention head. So what happens? The cost blows up. It becomes computationally very expensive, which is why people have been very sensitive to the flops, the floating point operations that are involved in all of these. Right? Now, what they are saying is that they're fine with that. They dared to use a lot of hardware, do all the computations, and said, let's see what happens. Now, knowing the neural scaling laws, you would have said, if you think back about the old neural scaling laws, what do they say? They say essentially, at least for NLP tasks, the bigger the model, the more the parameters it has, the more number of tokens, word tokens you train it on, and the longer you train it for, generally, the more the more powerful the model becomes. It performs well at the tasks, known tasks, but at the same time, it develops new abilities. It begins to do things that smaller models simply cannot do. Now, one of the interesting observations of this paper is that it shows that a similar behavior seems to be happening in the computer vision space, at least for these Sapiens models. Right? When you scale up and you are dealing with 1.2 trillion tokens, you realize that you are really training a vision model at an unprecedented scale. Right? Big model, lots of training data. So it has all the flavors of neural scaling here. All the telltale signs of a good neural scaling taking place here. So just reading this and being familiar with the neural scaling laws, I suppose you would develop an anticipation that they should blow all the prior models out of the water, isn't it? When it comes to the benchmarks, it should quickly become the king of the hill, at least in its specific task domain, namely human faces, the human images. And as we will see, it does actually do so. For fine-tuning on human-centric tasks, we use a consistent encoder-decoder architecture. So that comes from the ME. The encoder is initialized with weights from pre-training, while the decoder, a lightweight and task-specific head, is initialized randomly. So what this encoder-decoder refers to, we will see in a moment, and this may be a good, after this introduction, may be a point to go delve into the MAE, mask autoencoders. So consistent with prior works, we affirm the critical impact of label quality on the models in the wild performance. So they say that, yes, these things matter, many other things matter. I will skip over all the many other things that matter, but observe something very interesting. I want you to, if you could please pay attention to this comparison of state-of-the-art pre-training vision models. Sapiens adopts a high resolution backbone on a large data set in the wild human images. Well, for Facebook, a Meta research group to say images in the wild human images. What do they mean in the wild human images? In the wild just probably means they just look into their own data store because they have gazillions of literally, if the company's name is Facebook, you should be extraordinarily wealthy when it comes to faces, images about faces, isn't it? So that sort of gives them, puts them into a unique position to build such kinds of models, right? So in the wild, I suppose it means all the images that they have, right? The billions of images they have. So we'll start with that. They create a new data set of 300 million images. So how do they do that? The way they do that is interesting. First, they take a billion images and then they say, like, for example, are people there? Are you sure that people are there? Human beings are there in these images. They filter down, right? But then they further filter down and say, so we'll come to that. They do some pruning strategy, like how many faces are there? Are you also seeing cats and dogs or whatever it is, right? They use certain criteria to simply put, try to create a 300 million data set size of, should simply intuitively put, good human faces, right? Good, not just human faces, but good human images. Then they build models. Their biggest model is 2 billion parameter model. To train it took 8,709 gigaflops of compute, right? Which is 8.7, I suppose, teraflops of compute, right? And the image size they are dealing with is 1024, which, if you notice, is a significant jump from the 224 that people are used to. Now, one thing they do point out that while prior models, for example, Dino, which also came from Meta Research, Facebook Research, and Dino 2, which are amazing, amazing models, but they're general domain models. They look at cats and dogs and houses and whatnot. But Sapiens is all about humans, only about humans. As the name says, Sapiens. Maybe some of you may have also read the book Sapiens, amazingly good book. Anybody here in the audience who has read the book Sapiens? Nothing to do with this, absolutely nothing to do with this research paper, but nevertheless,
I did, Asif. It's Obama's most favorite books.
Oh, yes, that's right. It's an amazing book. Amazing history of human beings as a species. So this is it. So it should give you a sense, guys, look at this. People have created specific models. You notice that VIT, people have tried to scale VIT to sizes even bigger than Sapiens, but these people have gone, because they're dealing with a very specific domain problem, namely the human domain. They have limited to 2 billion, which itself is huge. In vision models, if you think of vision models are usually not as big as NLP models, natural language processing, textual models. Textual models are bizarrely big these days. 400 billion parameters, trillion parameter models, the humor is either already there being used in the frontier models or likely to be there soon, whatever. Vision models are usually a few orders of magnitude smaller. So 2 billion is actually extraordinarily big. So what are the key contributions in the paper? This is important. The key contributions are that we introduce Sapiens, a family of vision transformers pre-trained on large-scale data set of human images. So remember, it is transformer-based, first thing to know. And it has been pre-trained on a large-scale data set of human faces. Really big data set. Next, this study shows that simple data curation and large-scale pre-training. So what you do is you take a simple architecture. You will notice that they take an architecture very, very much like their prior work. Literally, they use the mask autoencoder, right? And to achieve this to a large extent. Just doing that significantly boosts the model performance with the same computational budget. Our models, fine-tuned with high quality or even synthetic levels, demonstrate in the wild generalization. They're better, otherwise they're not going to be much use. So what they're saying in the third point is they were able to create a meaningful model, right? Really great contribution. And the next is the first 1K resolution model that natively supports high fidelity inference for human-centric tasks. So it isn't anymore those tiny little 64 pixel models or 224 pixel models. Right? They really went 1,000. First time you see a model trained on 1,000, right? 1024 pixel. Of course, implicit is 1024 by 1024 pixel. Pretty big images they're training from. Now, let's stop here and think, what would a high-resolution image give? A high-resolution image will give us a lot of contextual data, isn't it? And transformers, at the end of it, attention is a way of creating contextualized vectors from input vectors. Right? To make it in the language of words, if you say he swam across the river bank, he swam across to the other river bank, the word bank takes its meanings from the variety of meanings that it could have. For example, it could have been a financial bank, it could have been a river bank, it could have been an airplane banking to the left or right. But when you say a sentence, he swam across the river to the other bank, that word bank takes its meaning from the context. Okay? So, and that is the job of the attention layers, the attention heads. They contextualize and give meaning to the tokens in some sense. Okay? Which for language is true, because in language, because they're homonyms, for example, quite often the meaning of a word is not so much in the word, but also in the context around it. The same is true for images. Suppose you see a tip of something. You have no idea what it is till you see that there is a dome that it is a tip of, right? And then that dome may not have much meaning till you realize that that dome belongs to some cathedral or some temple or something, right? So contextual meaning, and I suppose that speaks to the attention nature. Now, I'll skip all of these things about prior work, etc. The only prior work that we will focus on is the masked autoencoder. So let's go for that. So method. So how did they go about doing it? This is interesting. We utilize a large proprietary data set for training of approximately 1 billion in the wild images, focusing exclusively on human images. I suppose in the wild for Facebook, often could possibly mean vast majority coming from their own data set, because notice the presence of the word proprietary. Right? The pre-processing involves discarding images with watermarks, text, artistic depictions, or unnatural elements. So in other words, remove the noise, obvious noise. Right? Throw away those images. Subsequently, we use an off-the-shelf person bounding box detector to filter images, retaining those with a detection score above 0.9 and bounding box dimension exceeding 300 pixels. See, guys, if you take 1,000 pixel, an image is not about a human being. If in one tiny little corner, there is a hint of a human being, right? You want the human being to occupy a substantial part of the picture. And also, your confidence that it is a human being should be something like 90%, right? You should have fairly high confidence or detection score that it is a human being sitting there in the image. So figure 2 provides an overview of the distribution of the number of people per image in our data set, noting that 248 million images contain multiple subjects. Right? So this is very interesting. Where is figure 2? Yeah, this is figure 2. So what they found is that in these images, only 17% of the images that survived in their 300 million data set have only one person there. Quite a few have two people, quite a few have three people, and surprisingly, more than half contain more than four people. And yet they worked with those images. They said, all right, let's go with it. Now, this figure 3 is very interesting because it shows how well the model will work. And it sort of jumps the gun in some sense, but I'll mention it because it's quite impressive. Let's read the caption here. Figure 3, Sapiens reconstruction on unseen images. And this will speak to the masked autoencoder. See, what a masked autoencoder is, you give it a picture, but you go and mask a lot of the pixels, a lot of the regions. And then you say, so look at this one, the first one. There is a pretty girl at the top left. And now look at the second image here. What has happened to that image? 75% of the pixels have been masked, isn't it? Right? It's a very high or masking ratio. You have gone and masked so much. And yet you're saying, and then you ask, okay, what is this? Right? And if you notice, this model is able to reconstruct the picture. If you look very carefully, and I will do that, can you tell any very obvious difference between the original image, let's say, original versus this is the ground truth, and this is the prediction, the reconstructed. So this is your Y, and this is your Y hat. Isn't it? And this is what you feed in. This is your input. Input to the model. I don't know, but I consider this very impressive. I hope you would agree. It is very impressive. Any one of these images, look at this. If you, in particular, look at this image and this image, and you look at the input, at least I couldn't see the mountains. Can you make out the mountains? And the fact that modern AI, these neural architectures, can with confidence see all of this, isn't it amazing? Right? It speaks to the power of the model that is under discussion. Right? Look at this. Likewise, the beach. Look at this image. This is your Y. Sorry, Y. Why am I not able to? Okay. For some reason, I have lost the sync. Okay. This is, oh no, my Y is jumping all over the place. But look at the image of the ocean, the beach, a family on the beach. And look at the masked image. To me, the masked image looks pretty hopeless. Nevertheless, the machine is able to reconstruct the original. Right? Very close to the original. It's very hard to tell where the reconstruction is not exact. Actually, the only spot that I could think of is if you look very carefully in this region and in this region, maybe there is a little bit of subtle difference. Right? Very subtle, maybe, or maybe it's my imagination saying it, that there's a little bit of a difference. Right? But you have to really look very carefully to see the differences. Right? So obviously, the model they have trained is doing an amazing job. Human beings can very easily see things about eyes. We are very sensitive to eyes. Evolution has trained us to zero in observing people's faces, and especially in the face, zero into observing their eyes. Right? Because if behind the bush, if you see two eyes peeping at you, and the face looks like a tiger, you better have very high ability to detect the face and then those eyes. So, which was that poem of William Blake, Tiger, Tiger, burning bright in the darkness of the night. Anyway, there's that. That's the aside. So here's the ground truth. If you mask 75% of the pixel, you notice this mask ratio 80%, 85%, 90%, 95%. See, by the time you get to 95% masking, tell me if you can make anything at all out of this image, the masked image. Nevertheless, it seems to have reconstructed the eye, one would say impressively well, considering that most of the eye and the iris is masked. Right? So it is quite impressive, actually. Look at that. Now, you might ask that really, but you must also say that if you were to play this game with words, it wouldn't work. In the textual domain, it wouldn't work. In the textual domain, just as a recap, if you think about bird, for example, you say the cow jumped over the moon. And you go mask 95% of the words. Let's say that you went and masked this, 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 and you gave it the moon. What's the likelihood that the machine can reproduce exactly the sentence? Very, very low, isn't it? Right. So in some sense, and if you remember the old details of the bird paper, yeah, you think more like 15%. Right? The norm is for text, for NLP, in other words, text, 15% masking is the norm. Right? But because images have a lot of contextual info, right? If you look very carefully, look at this image. The second row, let's see where this thing is. At 75% masking, you can still see that there is a human face, isn't it? So what happens is that because there is so much contextual information, visual, locational information, or relative information, with images, you can actually get away with 75, 80, 85, 90, 95% masking, and still the mask autoencoders are able to reconstruct it, right? And those mask autoencoders are very much exactly the same sort of transformers and BERT-like architectures. They are VITs, right? And we'll come to that.
Hey, Asif.
Yes.
So what they are passing here are the training images masked. What happens if they pass in before unseen image and mask it? How good are they in that case?
Oh, yeah, that's what I'm saying. They are very good. They point out that the generalization is very good. Once you have trained the model, the ability to reconstruct, I mean, that is very good. In fact, if they couldn't, then you would say that it has just overfit onto the data.
Are they showing any examples of that?
They have literally this figure 3, if you observe this crucial word, Sapiens reconstruction on unseen images. So these are the images on which the machine was not trained on.
Oh boy, I don't believe it.
Yes, it is most impressive, and you better believe it. I mean, this is one of the most prestigious and high-powered AI research labs, the FAIR lab, right? This is FAIR, coming out of FAIR. I'm pretty sure this is a FAIR paper. Let me just see. Yeah, it's a Facebook. Right? Yeah, yeah, it is. Yeah, it comes from the FAIR labs. Yeah, yeah. So that's why I thought this paper
So
is.
Asif,
Go ahead.
so the input to MAE is the mask image and the Y hat the ground truth.
Exactly. Now, why is the ground truth? Y hat is what it reconstructed, right? In machine learning, whatever a model produces, it wears a hat. Whenever you see a
Okay.
hat,
Yeah.
it means that's what the model produced.
So Y hat is produced by our MAE.
Yes.
So what does it does with the input and reconstruct images?
Just say that again, please.
So what does it does between the input and reconstructed images to find the
Yeah, how does it do it? So that is the part that I'll describe. How does this magic happen, right? You would want to know, isn't it? This feels almost like magic. So how does this happen? We'll come to that. So before I come to that, let us just go ahead and assume that it can be done. Let us read the pre-training part. So remember, guys, if you build a foundational model, and just in the spirit of the old bird paper and all of these, what is the general process? You first create a foundational model, a pre-trained model. Once you have a pre-trained model, then you take a bunch of downstream tasks and effectively you create fine-tuned models for each of the downstream tasks, because each of the downstream tasks will have its own loss function. And so you can fine-tune the foundational model for each of those downstream tasks, right? So that is your classic paradigm these days. So let's look at this pre-training. By the way, you must have realized that we are doing something, these guys are doing something at an unprecedented scale, 1,000 pixel by 1,000 pixel, right? And how do they do that? Let's look at it. We follow the masked autoencoder, MAE, that I've been speaking about over and over again for pre-training. Right? Our model is trained. So for the time being, just take it that MAE contains an encoder and a decoder. Masked autoencoder means autoencoders have an encoder, decoder, right? In tandem. What input goes into the encoder, output comes out of the decoder. What the encoder produces feeds into the decoder. Well, not exactly, but we'll come to that. There's more to it. Right? We'll come to that particular detail shortly. Our model is trained to reconstruct the original human image from its partial observation. So now you realize that the actual tasks that they are going to do are a pose detection, segmentation, depth prediction, and normal, finding the norm in an image, right? At each point, which way is the normal vector going, right? None of these four things are you pre-training the model on. The unsupervised pre-training is not on those four tasks. And this is, if you go back and look at the original papers like BERT, etc., it's in the same spirit. You don't pre-train the model on a real use case. You pre-train the model to somehow understand the semantics, understand images generally. So what do you pre-train it on? You pre-train by taking an image, masking some areas and asking, fill in the blanks. What did I mask? Right? That's what you're talking about. Like all autoencoders, our model has an encoder that maps a visible image to a latent representation and a decoder that reconstructs the original image from its latent representation. There's more going on, so I'll skip it because I'll explain it in detail. Now, one of the things they say that their token size is very small. Each patch is just 0.02% of the image area, right? So is because it's a very high resolution image, right? And what it does is when you take so many tiny little tokens and they all pay attention to each other, you can get very fine-grained inter-token reasoning. And this sentence is important because you're taking such a high, and simply because of the high resolution, this statement becomes important. Each patch token in our model accounts for 0.02% of the image area. That intuitively a minuscule part of the image area, right? So what does it mean? Therefore, it means there'll be lots of tokens. And this provides a fine-grained inter-token reasoning for our model, right? So it will have a lot of contextualization of each little patch with respect to other patches, right? Remember, in the language of vision models, a patch is a token. Vision transform. So the patch is a token. Right? In natural language processing, roughly speaking, a word or a word piece is a token. right? For example, the word gold is a token. Now, 2D pose estimation. How do you do 2D pose estimation? So for 2D pose estimation, they actually make two interesting additions. First is that people talk about something called key points. Like in the computer vision literature, you will often see a mention of key points. Key points are the important points. If I can detect where is the nose, tip of the nose, where's the beginning of the nose, etc., line of the nose, where's the eyebrows, where's the lip, etc. So those are called key points. Right? Those pixels, which are highly relevant, right? That represent certain coordinates of the face, or features of the face. So these people have taken a fairly large, the largest one they take is 3 or 2, right? Large number of points. And what you will see is that compared to existing formats, which use at most 68 facial key points, our annotations consist of 243 features. So when they were training a posed estimation model, they actually annotated this highly. Now it comes at, okay, how do you have somebody sit and make those markings, annotations in an image, especially if you have to fine tune a model. And the thing is, they use a synthetic generation process, which we will not go into. But assume with these key points, we manually annotated 1 million images at 4K resolution from an indoor capture system. So they took people literally, and then they had them move around, and they took lots and lots of pictures. Body segmentation. Once again, they took a vocabulary or a dictionary of 28 things, like hand, face, nose, eyes, eyebrow, this, that, right, for segmentation. And a depth estimation is how deep it is. There's a little bit of mathematics, very straightforward. The average of the squares minus the square of the averages. It's a very common formula for depth estimation loss functions they're taking. And then similarly for normal representation. So there's more details in this paper. Now let's get a little bit into the implementation detail. And there's one sentence that is worth noticing. Yeah, and by the way, this is a typical loss normal. Similar to the loss is only computed for human pixels in the image and is defined as this. Like if your predicted normal vector is going like this, let's say, this is common sense, right? This term. Let's say that the real normal is this direction, right? And your predicted normal is going in this direction. So how much is the mistake? This is the difference between this, right? This is n naught, and this quantity is this, isn't it? And so the size of this vector is a measure of the loss, because if n hat pointed in the direction of the true normal, then that would have been 0. And then the second thing is a dot product. You take the normal of the dot product. Why? That's another term you add, because if n and n naught, n hat, are in the same direction, what is n dot product with n hat at that moment? It would be 1. So 1 minus 1 would be 0, right? So this is the explanation of this loss function. Common sense there, right? And so here are the technical details. Our largest model, so they train models of different scales, but let's take the biggest one, Sapien 2B. It is pre-trained using how many GPUs? 1,024 GPUs. 1,024 100 GPUs for 18 days using PyTorch. So obviously, that's a massive research investment or commitment. Now, these are the things that may be interesting, especially just yesterday, we were talking about the importance of learning rate schedulers and optimizers. Anybody here who was there in that session? Right? if you were there, then this will be very important to you. Observe how they make it a point to mention that they're using Adam W optimizer, right? So this is a exponentially moving average based momentum optimizer. The learning schedule includes a brief linear warm-up followed by cosine annealing. So what does it mean? Linear warm-up means slowly the learning rate goes up. Learning rate, if T is the epochs, learning rate goes up and then does what? Does like this. It keeps going, oscillating. So a gradual learning rate warm-up makes sense, right? A brief linear warm-up of the learning rate. Why? Because you start small, and then as the epochs are happening, the steps are happening, you bring up your learning rate. That you would expect that, okay, let's do that. Let this system sort of pick up speed, right? If you were to think of it as a car, right? It's gradually ramping up, driving on and ramping up. And why do you do cosine annealing? For those of you who were listening to us, it's very apropos of the discussion we were having yesterday. So I don't know, would somebody like to volunteer the answer? Why is a cosine annealing a good idea for pre-training the model? Like the big part of the training, coming up with the pre-trained foundation model. Why is it a good idea? What does annealing give us? It gives us escape from local minimas, right? So cosine annealing, annealing is to give you the intuition of annealing. You take a piece of metal, let's say you take steel, and you must have seen blacksmiths. Well, nowadays nobody sees blacksmiths, but the way you forge steel, you make it extremely strong, is you successively heat and cool it. You heat it up, comes out red hot, then you hit it, pound on it, pressurize it. And what happens is that the crystal defects, whenever a liquid sort of condenses, you have a defect. So there will be different nucleation points. So one zone, the crystallization may be pointing in this direction. Another zone crystallization may be pointing in that direction. So you have this defect boundaries. One microcrystal like this, one microcrystal like this. And when you have that, it's a weak material. What you want it to be is a complete lattice, long-range lattice. The more it resembles a long-range lattice, the stronger the same material, right? So you can take exactly the same compound, and by decreasing the defects and therefore having long-range lattice structure, you get much stronger material. That is what happens in physics and solid-state physics. Right? And that is the annealing process. That's why you see blacksmiths will heat up something, pound at it, and then keep pounding at it till it cools down, as it cools down, and then put it back into the fire. Right? So you reduce the number of those crystal defects and you create longer range order. Same thing happens in local minima. If you're trapped in local minima, so imagine that you're trapped in a local minimum here. And you have a tiny gradient. Let's say the gradient of the loss is some tiny amount, 0.03. I'll just take this as an example. What will happen? At this moment, if your learning rate is small, are you making progress? You're not making much progress, right? You're basically trapped in here. So at that moment, suppose the learning rate begins to climb up. What will it do? You remember that you're multiplying the gradient with the learning rate. That is your update. Delta theta update to the parameter is this. So if the gradients become very small because you're in a local minima, one easy way to jump out of or escape a local minima is that the learning rate increases. And that is why it is a very close analogy to annealing. That's why the word annealing is used, cosine annealing, that you successively heat and cool it. Right? for pre-training. And for fine-tuning, because fine-tuning is a very simple process, what you do is a linear decay. I mean, that is about as simple a linear rate, learning rate as you can do. So for fine-tuning, what they're saying is that it's a very simple process. So take a linear, this is the learning rate, and just linearly decrease it down, right? And it turns out that that is good enough. Now you can say, why didn't you do exponential decay? Why didn't you do stepwise learning rate, et cetera, et cetera? Perhaps they could have used, but their empirical judgment must have been that, hey, linear decay works just fine for that simple task of fine-tuning. All the models are pre-trained from scratch at 1024 by 1024 with a patch size of 16. So the patch size of 16, of course, it would ring bells of the VIT paper. If you remember, the original VIT paper, which brought transformers to the world of computer vision, literally had a patch size of 16. Right? So for fine-tuning. So the rest of it I won't go into. Suffices to say that, and I'll give you the benchmark, but the big mystery that I still have to solve is what exactly are those autoencoders? But suffices to say that when you look at the benchmarks, it is thoroughly impressive. Right? Look at the pose estimation benchmarks. Do you see that it is doing very, very well in almost all categories? It sets a new record for body, foot, face, hand, whole body, everything. It sets a new record. Likewise for segmentation. So segmentation is what? Detecting where is the hand, where's the head, and where's the this, coloring each of those things, right? And it does a very, very good job here too. It turns out, look at this result and compare it. Now here, for RMSE, the smaller is better. Right? The lesser the error, the better. Right? And absolute and relative and so on and so forth. So let's go. A depth estimation. Just the pictures tell you that the depth estimation is very good, isn't it? If you look, for example, at this picture, you can literally visually inspect which things are in the front and which are in the back. The head is leaning forward. The head is bright. The hand is leaning forward. The hand is bright. Isn't it? The foot is... Yeah, go ahead.
How was that achieved, though? I still don't get how they figured out the depth.
Oh, okay. So we'll come to that. See, there are two things. First is how do we train it? And the depth, see, ultimately, it's all a magic of the loss function. So let's go over that a little bit. So let us say that you know the ground truth. Let's look here. Suppose you know the ground truth, right? So you would imagine that, and you predict the depth, right? So you might be inclined to take d minus d hat as the error. But it is customary in computer vision for reasons that you don't take it like that. You actually take log of d over d hat, which is this expression. And so this is your delta D. This is the level of error that you made in the depth estimation. And from this, you create two secondary variables, the average depth across all the points for that picture that you have depth information versus the average of the depth and the average of the squared depth. Once you have this, this is known to be a good loss function for depth. And once you have this loss function, all you do is in fine-tuning stage for depth estimation, you go on, sorry, and we'll come to that. What you do is, and in the case of a mask autoencoder, there's an encoder and a decoder. You in fine-tuning, let's say for depth estimation tuning, you never touch the encoder. Encoder stays frozen. Right? So encoder, it stays frozen. This is a snowflake symbol to say it's frozen. Then the decoder, only the decoder gets fine-tuned with this loss function. That is it. That is it. That's all you do. And so you will have a depth estimation model. Right? And it does very well, actually, surprisingly well. Yeah, I mean, one of the most magical things in all of this is you just write a simple mathematical equation to quantify your error. And then you go on training these machines. And a few, like in this particular case, 1.2 trillion tokens later, the machine has somehow figured out how to do well with depth estimation. So that is that. Likewise, body segmentation, it does well. Then surface normal estimation, it does well. Right. By the way, observe something very interesting. When people talk of depth, they not only talk of depth, they also talk of the gradient of the depth, like how strong, how steep is the change of depth. Like when you're doing ocean studies, of course, it matters, right? How steeply is the depth changing, right? So, and if you look at this picture, if you pay attention to, it's quite amazing. You can literally see areas where depth changes rapidly. Right? So gradient of the depth, right? Depth, anything, and so forth. So look at this and look at this here.
It's like a 3D image.
Yes, practically a 3D image. It's amazing, actually.
What I'm noticing is that there are no, I don't know how I should say, no black people in the images. I wonder how the model will perform on, for example, a black person.
Why don't we experiment? So we'll end our talk by actually playing around with those. There's a demo, and why don't we feed that in and see what happens? We'll do that. So suffice to say, and here, this again to the neural scaling law, the number of images you give leads to better performance, etc. So Sapiens, in other words, this is a good model. Now, the one thing that I left out is that this rests upon our MAE. How does our MAE work? Now, let me talk a little bit about the MAE. Let's take this as a context. And MAE, masked autoencoders. So to mask autoencoders, I actually brought that paper up. And why don't I use that for a very short explanation of that paper? Suppose you take a flamingo. Here is your flamingo. What you do is, and this picture actually says a lot. You cut the picture out in masks, right? And suppose you mask out 75% of the masks. So what does it mean? Only 25% of the patches will remain? Here is something interesting we do. And I think this picture will convey the whole of it. Are we feeding all the patches here to the encoder? No, we are feeding in how many? If you really count here, 1, 2, 3, 4, 5, there are 25 patches here, but we are feeding in only 1, 2, 3, 4, 5, 6, 7, 8, 8 patches. The patches that have not been masked, the real patches. You feed it to the encoder. What will the encoder do? It will give you contextualized patch vectors. Isn't it, guys? Right? You take this image. I hope I'm making sense here. We take this image and you take this image. In this image, observe that we have masked out of the flamingo. So much of the information has been masked out. Right? And you just give it to the machine only the unmasked patches as tokens. And encoder, by the way, a transformer encoder, what will it do? A VIT. What will a VIT do? Encoder will do what? It will produce for you the encoded, the contextualized vectors, embeddings, isn't it? And once you give this embedding, now there is an issue here. What you do is you take these embeddings, but you remember their position. You remember that there is first this guy, then this guy. So this guy comes here, this guy comes here, and this guy comes here. Do you see how it goes? You take and create, let me just call it the embedding E. And then here, this is the input to the decoder. Again, a transformer-based decoder. Why should it be? Because see, the only way the encoder can make head and tail out of these little patches is try to figure out by understanding other patches, isn't it? Any one little patch will keep asking, what am I? What am I? And its best hope is to pay attention to the other patches. Right? Once you have the encoded patches, you give it, and now to the decoder, you are giving more. You are giving not just those patches, but you are giving this blank, all the masks. Now, why is that important? Because in the mask, you contain, so this mask will be some learned vector. So all of these masks will be some learned vector. Let me just call it M vector. Let me just call the masked vector some M. But it also contains the position 1, M2. You see that, right? And this would be whatever came out, right? E1, embedding 1, position 3, and so forth. M, position 4, M, position 5, M, position 6. And then here comes vector, the second vector, E2, at position 7. So you're injecting position awareness and you're feeding it some learned vector. Just some judiciously, some machine figures out what is a dummy or placeholder vector you can feed into signify that I represent a mask. M vector. And is learned vector. During training, the machine figures out what's a good one. Now you again give it to a decoder network, again a transformer network. What will the transformer network do? It will transform each of these tokens into yet another vector, isn't it, guys? Input vectors goes out, transformers, and output vectors come out. Exactly the same number. And then what you do is you reshape these vectors because you know that they can be treated as patches. You reshape the patches into a square image, and beautifully, you know that the target should be this. So if the machine produces something else, what do you have? You have a loss. So this is your Y. If the machine produces something else, let's say it produces Y hat, what can you do? One of the easiest losses you can produce is just MSE loss. Isn't it? You can just go with the MSE loss with respect to the pixels. And so you can go on training this machine. Now, there are subtleties to it. I mean, this paper is a very, very interesting paper, and the title is very nice. It says, masked autoencoders are scalable vision learners, right? It was quite, again, came from FAIR Research, the FAIR Research group. What it did is it showed that you could create autoencoders with transformers quite well. Now, observe something interesting here. You may ask, why did I not pass in masked tokens here also as an input to the encoder? And the answer to that is quite interesting, actually. What happens is the fewer tokens you feed in, input tokens are just placeholders. I mean, masked tokens are just placeholders. To the encoder, by giving it only the meaningful tokens, only the meaningful patches, you realize that you have reduced the quadratic complexity of the attention, isn't it? So let's say that this is 25 by 2, this is 5 by 5, 25 patches. Instead of 25 patches, you're giving it only 8, 1, 2, 3, 4, yeah, only 8 patches. So you would agree that 8 square is 64 and 25 square is 625, right? So almost by a factor of 10x, because you do KQ, B, but this quadratic term, which is now a 10x less expensive, isn't it? In the attention head, it's 10x less expensive. So because it's computationally efficient, what it means is that the encoder, you can actually have, where should I draw it out? Maybe I'll draw it out here. This encoder, you can actually make it deep. Attention, attention, attention. You see that, right? You can make a pretty deep and powerful encoder with transformer, with transformer layers, attention layers, and lots of feed forwards in between. So in other words, you have the luxury of using your parameters efficiently, right? On the other hand, the decoder, the experience shows, and I won't go into all of it, the decoder is pretty lightweight because it's not doing a lot of heavy lifting. It's just trying to fill in the blanks. Right? So this was the famous mask autoencoder. This introduced the mask autoencoder from a transformer perspective. If you remember, a mask autoencoders have always existed. You could create like this autoencoder using CNN also. But the problem with CNN is, in CNN, you don't have position encoding. It's very hard to inject, right? So you can't create something like this. You can't play this game so easily with the CNN. So, and there's more into this paper. Let you go read this paper. So this is the explanation of what we are looking at. Now observe that in this paper, when they do it, this was 2021, realize that the gap between what the machine reconstructs and what the reality is significantly different, isn't it? This is pretty unsatisfactory compared to the ground truth, right? So, well, time has passed, and now you have Sapiens, at least for humans, you see that it does an extraordinarily good job, right? And so the message is that you need to scale up your model. It was because those models were too small. The ones being used at that time were too small. Now, that's the paper reading part of it. Let's try and see whether this is true. One of the questions that someone raised is that none of these people seem to be Afro-American. None of them seem to be Indian either. So would you like to try it with one Indian face, South Asian face first?
There was a couple of people that were darker, but...
Yeah, no, there is a South Asian face available right now. Let's try that. Let's try this one. And see if we get, oh, here we go. Should I try this one?
Go for it.
Did it take a picture? Let me see. There we go. And let's run it on this picture and see what happens. What do you think?
Very good.
So this speaks to the generalizability of this models, Sapiens models. It seems to do it very well, isn't it? Right? Though I wish it had showed me with broader shoulders. No, I'm kidding.
But in this case, it took your photo. So for the model, it is totally
Completely new. It's unseen
new,
data.
right? It's unseen, right?
It's completely unseen data. And therefore, the evidence that it generalizes.
But what would have been the input which has gone into the model from your photo?
See, this is one of the things, the input from my picture,
Yeah.
the entire picture. The entire picture was the input to the model.
And it has
Detected the pose. It was
Yeah,
a
it
pose
was-
detection
it was a
problem.
pose. Yeah, for sure.
Right. Let's see how well it does for the segmentation. And I will
Oh,
copy that along. Okay, now let's how well it does segmentation. So I just, in the interest of speed, I may choose to just pick one of these models. Or would you rather again take me? Let's take this. There we go. Where did the image go? Well, somehow it's responding very slowly. I think the Hugging Face website at this moment is responding a bit slowly. So it is responding, but okay, it is bringing it in. Let's try our luck, how well the segmentation works. Oh, look at this. Did it get the face, the lips, etc. right? It seems to have gotten some parts wrong, like the cloth. It is mixing up this
The
microphone,
microphone, yeah.
yeah, with the t-shirt. So there is a bit of error. It got my hair quite well. And the lips, it was supposed to detect the lips. It seems to have done that. It has found my left upper arm here. That also is right. And the face seems to have gotten face and neck to be this, which also is right. So yeah, this is it. In the lower lip, where is the lower lip? Is this color, or the and it seems to have gotten that one right. So there we go. It does seem to have be getting it right. Let's see how well it does with the depth perception, because behind me is considerable depth, but it will do the depth only for the human part. Let's see. Input image. Oh, it's because it hasn't taken a picture yet. I think it takes some time. Click to access. I did that. Oh, something is happening. Let's wait.
Why didn't you use that image with the White House behind it, or whatever that is from
Oh,
the selection?
That should be a tough one. Yeah. Okay, I'll let you decide whether this is correct. I think it is correct because I am standing at a slant. So this is actually my forward part. And this is a little bit away from the camera. So it has gotten the depth right. But yes, let's go and give it that. Where's that image one? White House. Okay, this one. Let's put it here. Where did it go? Oh, here. Yeah, let's run that. Remember, it will do it only for the human body. It won't do it for the background. Yes, the hand is sticking in front, isn't it? So it has gotten it. So the results are pretty impressive. And that, I hope, was a fun paper to read. I hope you liked it. Any comments, guys? Anything else anybody would like to say?
This is excellent. Yes.
Yes. Now, if only we had a A100 in-house. Oh, yeah. And a few thousands lying around would be even better.
We need to go work for FAIR. You seem to have a lot of money.
Yes. So I'll
Yeah, you're still recording, Asif.
yes.